Everyone, welcome back. In today's explainer, we're tackling something that honestly feels a little bit like modern magic. We're going to look at the exact process of bridging that massive gap between digital logic floating around inside your computer and the actual physical reality of a hardware board. We're breaking down the FPGA configuration process step by step. So let's jump right in.
Now you might be wondering, how exactly do you take a few lines of digital code, just sitting there on a screen, and turn it into a physical, blinking light in the real world? It's kind of a fundamental mystery when you're first starting out. Well, the answer lies in a really specific configuration workflow using Quartus software. It basically acts as our bridge, translating our abstract ideas into hard physical instructions.
To build this bridge, we've got a quick four-part roadmap today. First up, we'll meet the DE10 Lite board. Second, the logic design phase. Third, assigning the hardware pins. And finally, JTAG programming and testing.
All right, step one, meet the DE10 Lite board. Right in the center of the action is the Terasic DE10 Lite board. It's a fantastic setup for learning digital logic, mainly because it features that powerful square chip right there in the middle, the Max-10 FPGA. Now, the absolute most crucial thing to grasp here is the architecture. Literally all the important components on this entire board are wired directly to the pins of that single Max-10 chip. It's a blank slate, letting us configure the connections exactly how we want them.
And here is a great look at what we actually have to work with. For simple experiments, we have this whole playground of tangible inputs and outputs. Down across the bottom right, you'll see 10 physical slide switches. Right above those, 10 individual LEDs. And over on the left, 6 7-segment displays. This is the physical reality we're going to take control of.
Moving on to step 2, the logic design phase.
So this whole phase happens entirely inside the Quartus Prime software. You start by creating a project, and right out of the gate, you have to tell the software exactly what hardware you're targeting. For our board, we pick a very specific Max-10 device. It's the 10M50DAF484C7G. Yeah, it's a bit of a mouthful. Once the software knows the exact chip, we move to design entry, where we write our code. Let's say we write a simple Verilog module for a two-way light controller. Basically, a circuit that uses 2 switches to control one light using an exclusive OR function. All right, once our code is written, we go ahead and hit this vital button, Start Compilation. This is where the magic really starts.
But wait, here's a massive takeaway for today's explainer. This very first compilation, it's entirely about synthesizing the logic. If you check the compiler flow summary after clicking that button, it'll tell you your two-way light controller needs exactly 3 pins on the FPGA chip. But at this stage, the software has absolutely no clue where those pins actually live on the physical board. It just knows, hey, I need 3 of them.
Which perfectly sets up step 3, assigning the hardware pins.
This right here is the core architectural blueprint phase. It's truly the most critical part of our whole workflow. To physically connect our floating digital signals to the board's hardwired pins, we use the assignment editor in Quartus, which ultimately saves everything into a Quartus settings file, or QSF for short. You can think of this QSF file like a giant address map. Because the DE10 Lite has fixed physical connections between the chip and its components, we have to manually tell our software exactly which pin connects to what.
Let's look at a real-world example of this mapping. For our little two-way light controller, remember we need 2 inputs, X1 and X2, and 1 output, F. Using the assignment editor, we explicitly tell it that our software variable X1 must live at FPGA pin number C10, which happens to be slide switch 0. Variable X2 goes to pin C11, which is slide switch 1. And our output, F, gets mapped to pin A8, which is physically wired right to LED 0. And here, you can really visually connect the dots. On the left, we've got the physical slide switches pointing straight up to the Max-10 chip. On the right, the exact pin addresses you need to reach them. Oh, and by the way, pushing a switch up sends a logic 1 to that pin, and pushing it down sends a logic 0. We are literally hardwiring our digital logic to physical reality here.
So here's the real kicker. Once you finish assigning all those hardware pins, you're actually not done. You have to compile the project a second time. This second compilation is absolutely crucial because it bakes those physical pin locations directly into your synthesized design. It permanently marries the logic you wrote with the actual physical addresses on the board.
All right, final step, number 4, JTAG programming and testing.
Now that our bridge is fully engineered, we use the Quartus Programmer tool to send it all down to the board. First, we set up our hardware connection using a USB blaster cable, which acts like a fast data highway from your computer to the board. Next, we select our .soft file. That's the SRAM object file, the final binary data holding all our configuration instructions. Make sure the Program/Configure box is checked and just hit Start. The green Load LED on the board will light up, and once it's done downloading, the Conf LED will turn on. And boom, your code is now hardware.
But before we wrap up, I have to share this fascinating little quirk about the process. 0. That is exactly how much of this configuration your board actually remembers if you unplug it. See, the board is configured in JTAG mode, which is amazing for quick testing and loading data, but it's totally volatile. The device only holds on to your brilliant design as long as it has power. The very second the power drops, the configuration vanishes into thin air and the board resets to 0.
And there you have it. That's the complete workflow. By mastering this meticulous process, from picking the device to the absolutely critical pin assignment phase and running that double compilation flow, you have officially built the bridge from code to physical reality. So now that you know exactly how to hardwire and control a single LED, what massive, complex physical systems are you going to build next?